Uh, this is Jim, and today I will introduce two applications in ecam function:
Yani
rotary cutting and flying cutting. And also, I will introduce the third way how to create the ecam curve. In last training, I have introduced how to create the ecam curve by software or by the move instruction. And today, I will introduce how to create it by ecam tbx instruction. This picture we have already seen it in our last training. This is the rotary cutting. Master is usually the feeding model, and the slave is the cutter model. And in each ecam cycle, the feed axis will move the one master length, which is the material's length, and the slave will perform a rotary cutting action. And this is flying cutting. Master is also the feeding axis, feeding motor, and the slave is the cutter. And also in each cycle, the feed axis will move the one master length, the length of the board, and the slave will perform a catch up, cut, and return application. You can check it with the ecam curve. Step one. Step one, the cutter will accelerate from the orange position and to the start point of the thick area. This point here is the and here. Step two, in sync area, the cutter will keep the same speed with the feed axis, the same line speed. And after cutting, the cutter will leave uh, deceleration from the end of the sync area and go back to the zero position and stop at zero position and wait for next ecam cycle. You can see in this picture, when the cutter rotate to this is the cutter. When the cutter achieve this area is sync area. In this area, the line speed of the cutter. This is the line speed of the cutter. This speed will be same with the feeding axis. So here on this point, when we cut the materials, the cutter will not damage the material. Okay. And this is the flying cutting. Uh, the step one, the cutter will stop at zero position and wait for ecam start. And step two, the cutter will speed up to catch the feed axis from this point. And when the cutter reach the sync area, the cutter will keep the same speed with the feeding axis and do the cutting action. And after cutting the the cutter will stop and go return to our 0 position. So here have and then wait for next start signal. So this is the steps of the flying cutting. And this is also another picture. 1, 2, 3, 4, 4 steps. Speed up, keep same speed, cut, and stop and go back. This is one cycle. Okay, so so now I will introduce how to get the rotary cutting curve. Before, first of all, we need to check this instruction. This instruction code ecam tbx. This instruction is used to generate the flying cutting curve or rotary cutting curve. And this instruction have four parameters. First parameter is the first address of this of the buffer table of this instruction. You know, in our last training, we also have another buffer table for the ecam instruction. And then second parameter is the type of the ecam curve we want to get. K100 is rotary cutting and the K101 is fly cutting. The third parameter is the first instruction, first address of the ecam buffer table. This is the ecam instruction. In ecam instruction, the second parameter is the first address of the ecam buffer table. So here we need to bind the same address. So we can combine this ecam tbx instruction to the ecam instruction. And the last parameter is the result of the of this instruction. If we get the curve successfully, then we will get one number, the number of the segments in D1 in this instruction. So when this value is bigger than 0, it means we have get our curve successfully. If the number of this instruction is smaller than 0, it means they have some error during we execute this instruction. And for details, X here, this is the error code. So when you get the error code, you can check this table to see why your uh, parameter is wrong. Okay, now let's check the buffer table of this instruction. Here, the first parameter is the master length, and second parameter is the slave length. Third parameter is the slave sink length. The master length is the material length. It means, for example, you want to cut one 20 mm board or 50 mm board. Then we need to set the master length in this parameter. But this parameter is post unit, so we need to convert the length of the board to the post axis, post unit, and I will show it in details later. And also, the slave length is for the rotary cutting. For the rotary cutting, if there is no reducer, and for single cut cutter, the slave length is the number, the PPR of our cutting axis. For example, this cutter is single cut because they only have one cutter on this road. And yes, And then the third parameter, select sync length, usually we set it as uh, about 30% of the select length. Because if we set for example, if we set the sync area too much, too long, uh, okay, check here. In this picture, the sync area is about 30% of 3600 degrees. If you set the sync area, for example, you set the sync area like this long. So it means during this angle, the cutter will have the same speed with the fitting axis. So it also means the cutter only have this very small space to adjust its speed. It need to accelerate or decelerate. But uh, if this space is too small, then maybe the driver have to have a very big acceleration or deceleration. So it will make problem. So we usually set 30% of the uh, whole whole slave length as our sync area length. Slave length 10,000 people. Yes, for our Java the default PPR is 10,000. So for example, if you use our Java as the select axis and didn't change the parameter, then the select length is 10,000 posts. Okay, let's continue. And here, the fourth parameter is the select sync ratio. What's select sync ratio? Because as I said, we need to have the same speed in sync area, right? But the PBR of the fitting axis and the cutting axis may be different, and also the diameter of the fitting axis and cutter axis will also be different. So we need to do some calculate to make sure in sync area the master and the slave will have same speed. And this is some form about how to calculate it. And and I will show it later with the parameter. And the next parameter is the max sync ratio. For rotary cutting, this parameter usually 5. It means in sync areas, the speed of the slave should be less than 5 times of the master length. For example, if you calculate the parameter 4 by some variable, so this parameter will take effect. But if you directly set the details ratio in parameter 4, then this parameter will not take effect because this parameter 5 is just to make sure the sync ratio will not be bigger than 5. Okay, and the next three parameter, acceleration curve, camp curve, and resolution. Resolution, we have introduced it in our last training. It's just the resolution of our ecam curve. And the acceleration. curve, we have two. In fact, we only have 0 and 1 setting. These four setting we don't support. The manual didn't update. And the 0 is the T-type curve, and the 1 is the S-type curve. Parameter 7, cam curve. Cam curve, different cam curve where we will get with the different cam curve, we will get the different location of our sink area. And I will show you with the picture later. For example, left cam, left for this cam, the sink area is on the in front of the curve, and the right cam, the sink area is in the back of our curve. And the last parameter is the sink area start position and the sink area end position. These two parameter we don't need to set it because after we setting after the after we set this parameter from parameter 1 to parameter 8, the parameter 9 and 10 will be calculated by PLC. So we don't need to set it. It will get automatic. And what we need to do is we need to move. We need to move these two parameter, sink area start parameter and the sink area stop parameter, start position. We need to move these two parameter to our decay instruction buffer address. If you remember, we also have the master master start sink area and the master end sink area. We also have these two parameter in decam instruction, so we need to move these two parameter to ecam. So let's when our master when the master achieve the sink area, we can have the sink signal output, and we can use this sink signal output to control our cutter or to control something. Okay, and now we can check this parameter in details with the details parameter. For example, here, this is our fitting axis cutter, and the red mark is, for example, is our ice mark. So here, the material length arrow. This is our master length, and how to convert it. For example, here we have arrow is 1000 mm, and D1, the diameter of the master is 100 mm. So here we use this form to calculate for example how many turns does the master need to rotate to move 1000 mm. And after getting this parameter, we also have PPR of the master axis. So here from this form, we can get the our master length is 3184. It means when our master driver move 3184 poles, this this will push the material to go forward 1000 mm. So this is the calculate of the master length. Do you have a question about this calculate? Okay. Uh, and the slave length is the PPR of our driver. Yeah. if you have for example, you have a two ratio reducer, and your PPR is 1,000 poles, then this slab length should be 2,000 poles because if you have a two ratio reducer, and also if here you have three cutter on or four cutter, for example, you have here four cutter uh, in one road, then you think your slab length will be this. So it is about 250 poles. And now we have only single cut and no reducer. So the PPR of driver is the slab length 1,000 poles, and the sink slab sink length we set it as about 33% of the slab length. So it is 333 poles. Uh, if the gear rotation of the slab is 110, then we need to set the slab length as 10,000 because the servo rotates 10 load will make this cutter rotate one load, and our slab length is the length of the how to say cutter rotate one load. So we need to make our driver rotate 10 load to make the cutter rotate one load. Okay, and let's check other parameter. Uh, this slab sink ratio. This parameter is how to calculate this ratio. First, we need to calculate uh, uh, these two parameter. What this parameter means? It means, for example, how many poles we need to send to make our make our load to move 1 mm. For example, here for master, if we want to make for example, this is the board. If we want to make the board to move 1 mm, then the driver need to send this is the post number the driver need to send. And also for the slave, if we want to control the cutter to rotate 1 mm, then we need to send the this this pulse to make it rotate 1 mm. So after we get these two parameters, we just need for example, this is parameter A and parameter B. Uh, the ratio is uh, equate to B divide A, and the B is the uh, accurate pulse number of the slave, and A is the accurate pulse number of the master. Don't miss, don't remember the order. It's B divide A, no, not A divide B. Do you have any question about these two form? Okay. So so now we can get our select sync ratio. It's about 1.66 and 7, and it is smaller than 5. So this parameter is okay. If this parameter is bigger than 5, we need to adjust the PPR of the master, or we need to adjust the PPR of the select to make sure the parameter the ratio is smaller than 5. Okay. And for these three parameter, uh, nothing to introduce in details because we just set it. You can use 0, t-type, or 1 s-type curve. But I will show you the difference with different cam curve, this parameter. In my program, I set it as 0, but I have already tested with the all cam curve, and I get this curve of the different uh, cam curve. We can check it. First, we can see this is our master length. It's uh, it's 300 and let me check. I forget. Okay, it's 3,184. Yeah, so we can see the master is all same, and then the slave is 1,000. You can check here 1,000, 1,000, and 1,000. So in these five, uh, okay, so in this five picture, where is our sink area? Uh, this range, this parameter is the start position of the sink area and the end position of the sink area. I get it from program from these two parameter, parameter 9 and the parameter 10. So here, for first picture, the sink area is here. And then the second parameter, the sink area is two parts. In these two segments, the speed of the cutter is same with the feed axis. And for the third picture, the sink area is at the end of the cutter, of the master, because you can see this parameter, 3,184 is the length of our master. And for this parameter, for this picture, and the first and the beginning of the curve is our sink area, and the last parameter, last curve, the sink area is here. So we can see with the different cane curve, we will get different sink area. Uh, yes. So I want to say is select we can select the suitable cane curve according to the installation of your uh, cutter axis. Okay. So and for example, if your cutter is like this, for example, your cutter like this, the zero position is on the top. For this installation, you can select uh, you can select left cam. You can select this left cam because at the beginning, your cutter is on the top, and we must running. Your cutter will speed up, and here and this area, in this area, your cutter will go to the bottom of uh, the bottom point and cut the material and go back uh, to the zero position and wait here. And when for example, next ice mark coming, it will from zero to speed up and cut and slow down and stop and zero position and wait for next ice mark signal. So this is one example. And if your installation is different, yeah, you may need to select different cam curve. Okay. And we can check the program. Let me check. Frying cutting. Let's open the Rotary cutting. Clean the memory and download the program. Uh, eh, okay. So here, uh, this this part is to get the Rotary cutting curve. Here I write one subrouting to corner cutting parameter. We can check it. Here this is our master length. Master length, slab length, and slab sink length. Master length, slab length, and slab sink length, and this sink ratio 1.667, and the max sink ratio 5, and the speed curve 0. 0 is T type, and the cam curve 0. 0 is left cam, and the last resolution is 300. So this is all parameter I set here. And now we set on M1 to get our curve. D100. You can see D100 here. My first address is D100. Sorry, D500. And the second parameter, K110, 100 means rotary cutting curve. And the third parameter is the first address of our DCAM instruction. Here you can see DCAM instruction. I use D1000 here. And the last parameter D50 is the result of our curve. The result is 301. It means we get our curve successfully, and then the totally point is 301. We have 3001 points to consistent to consist of our ecam curve. And now this part is our DCAM instruction. And I use the Rotary encoder, AB phase input, and Y0, Y1 output. Here the the DCAM I set it as periodic pre periodic ecam and start from current position, and I enable the sync signal and output Wi-Fi is setting by this parameter. If you remember, this start methods, uh, 64 is from current position. I have introduced it in our last training, DCAM, and also set this. Uh, this is this D1004.0. This is the bit 0 of D1004. So we set on this one. This is the flag to enable the sync output signal. And this 1005 K1 means priority ecam. And 1008, this parameter is the sync terminal. I set K5, so it means Wi-Fi. And now we run the DCAM instruction. And here we can see our sync area is between 400 and 599. And now I will rotate the master. Okay, you can see with the master going, the slave will come. And now we achieve our sync area. Okay, you see here, when the position of the master is bigger than 599, the sync signal will turn off. Okay, and continue. Now, you can see here the slave achieved 1000. So it means our slave have already finished it. It is not this curve. Here, first curve, left cam. It means our slave have already achieved this point, and it will stop at 1000 position, and until the master finishes. So here, our master length is 3184. Okay, so now our first cycle is finished. And now when the master continue to go, you can see the slave is also running again. And here, achieve the sync area. So now we can cut the, for example, package. Okay, so this now another cycle coming, another cycle. Okay, so this is the Rotary cutting instruction. You can see, in fact, it's very easy to design Rotary cutter curve. We just need to calculate the master length, slave length, and calculate the slave sync ratio. This three parameter is a lead. We need to calculate. And other parameter, for example, the acceleration curve and the cam curve or resolution, we directly set it. We don't need to calculate. So this is the instruction about Rotary cutting. Do you have any question? Okay, I think I can continue to introduce uh, fly cutting, fly cutting curve. For fly cutting curve, in fact, it's the steps about how to get the fly cutting is very similar to Rotary cutting. And we can check this example. And also, this is our master axis. Example is also a wood board, and the right part is our F mark. So L1 is our master length, the length of our board, and we can check this part. This part we have one driver to rotate this uh saw, and this saw will make our cutter. This block is our cutter. A B C D means four position. So our cutter will start from position A and achieve position B. Position B and position C is the sink area start position and the sink area end position. And D is the return position. So it means when the cutter achieve B, will go back. So here we have three legs. Master length is our material length. It's same with the rotary cutting. And for example here, stoppage is 20 mm. It means when it's our slave rotate one load, our cutter will go forward 20 mm. Okay, and the slave length here, the slave length is uh, L2 from A to D. Yes, and then the sink area, understand, we set it about 33% of our sorry, here perimeter is wrong. We check. It's 100 and 33. Okay, okay, they can continue. And for example, the master and the slave, the PPR of master and slave is 1000. So first, let's calculate the master length. It's then because the diameter of the master is 60 mm, so we put it together with pi to get the uh, how to say, I forget that uh, to get this to get the length of this road. And we use the master length to diverge to divide this. So what's the result? This result means how many uh, how many roads does our master need to rotate to make our board go forward 660 mm. And after we get the number of the loads, we calculate with 1000 ppr, then we will get the total pulse that the master need to rotate to push the uh, material to go forward. Uh, okay, and for the slave length because here the stop pitch is 20 mm, So it means when the driver slave driver rotate one load, our cutter will go forward 20 mm. If they have no reducer, if they have reducer, we need to uh, de to calculate it with our reducer. So here, after calculate, we can see the slave length of our uh, the result of our slave length is 5,000 poles. So our slave sink length is 1,667 poles because usually set it as uh, sorry, because I changed the parameter, but some place I forget to change. Okay. Yes, it's correct now. So our slave sink length is about 1,667 poles. Next part, we need to calculate the slave sink ratio, and the calculate method is same with the rotary cutting. So here, uh, you can just check it, have a look at it, and after calculate, we can see the sink ratio is about 9.4 9.424. The limit for the usually the limit for the rotary cutting is 5, but for this fry cutting, we don't have that limit. So this result 9 is okay. 9.424 is okay. And we can see for other parameter, it's also same. Acceleration curve. Here I select one. One is S type S type speed. But for can curve, for can curve, uh, for fry can curve of the fry cutting, we only support one type. In fact, this parameter don't take effect. You set it as one, as two, as three, where we get the same curve, and the curve is default as right cam and left cam to constant, the constant of our frying cutting cam curve, and the resolution is also 300. And this is the curve I upload from the software. So here the master length is 300 and sorry 3,501. So here you can see it's 3,500 about. And for the slave length, you can see here is 5,000 here. Our slave length 5,000. And then the slave sink length, you can see in fetch here. Our sink area is about an this patch 1,000 to 1,200 and 1,400 about this patch. So it means when the master achieves this segment, here the speed of our slave is same with the master. So we can do the cutting action in this area. Here we have one point need to uh, take notes. Let's go back to here because for frying cutting here we must have enough time for our cutter to go up and go down, right? For example, this time maybe 1 second or 2 seconds. This speed we can't this time we can't change it. So it means we need to left enough length L3 to make sure our cutter will have enough time to go up and cut and go down, right? If the time is not enough, we need to add. You need to increase the length of L2. So, or you can maybe set 50% here to make sure the length of L3 is long enough to make sure your cutter have enough time to cut. And when you calculate it, it will also be affected by the max speed of our encoder, of our master model. Because when the speed of our master is faster and faster, the speed of our slave will also become faster and faster. So it means the time to go through B and C will be less. And if this time is less than the time we need for cutting, it will have a problem. So we may need to reduce the master speed, or we need to add the length of our L2. Okay, so this point we need to note it. For rotary cutting, we don't need to note it because here the cutting time is very short. Maybe because the cutter just need to touch the cutter, and we'll finish it in the cutting action very soon. But this frying cutting is different. We need to have enough time to cut. And for the program is we can check the program. The program is similar with the rotary cutting. Let's open this fry cutting. Clean the alt curve. Don't run a project. Okay, and here set I use this curve parameter, this subloading, to set the master length, slave length, and all these parameters we have calculated each in our presentation. And here to call the default value and get our curve. Okay, now we get our curve successfully. And for the ecam, instead I use priority ecam and start from core range position and run it. And you can see the sync area. Sync area is between 1000 and these two value. And now I will rotate the master. You can see at the beginning, our slave is stop in zero position, and now begin to speed up, and now achieve the sync area. Now the cutter will go up and go down and go up and cut and go down. Now leave our sync area. You can see here when the slave achieved 5000, it will begin to go back and stop at zero, and our material continue to going. And now next cycle coming. Okay, you can see the position of the slave. It will go to 5000 and go back and wait. And our master is continue running forward. Okay, so this is the fry cutting. How to get the fry cutting curve. And for example, if you want to check the ecam curve you can read the program from the PLC. First, you need to download the program and get the uh, get the position, get the curve by this instruction, and you read it from PLC. And here, check this electronic cam table and set the start position. Now we are in our program we use D1000, so here we select D1000 and read it. And now you can check your ecam curve here. This is the ecam curve of our master and slave. But here we can only upload the position information, the speed position and the acceleration information of our slave. We don't support to upload. Okay, so this is our today's training about these two application, rotary cutting and frying cutting. Okay, and then the time is late, and you can have a rest. And thanks for your attending. See you next time. Bye.